Have you ever wondered how particles can change their behavior when they are observed? Welcome, curious minds, to an exploration of the baffling world of quantum physics, where the rules of classical physics take a backseat and the bizarre takes center stage. Quantum physics, in essence, is the study of the very small, the atomic and subatomic level of the universe. It's a realm where particles can exist in two places at once, pass through solid barriers, and even change their behavior when observed. Yes, you heard that right. Particles, it seems, are quite conscious of their surroundings. One of the most mind-bending principles of quantum physics is the wave-particle duality. This is the idea that particles such as photons, electrons, and even larger atoms can behave both as particles and as waves. They can exist in multiple states at once, only deciding to be one or the other when they are observed or measured. This is not a concept that we can easily grasp, for it defies our everyday experience of the world. But it is a fundamental aspect of the quantum realm. Now, let's dive a little deeper into the rabbit hole with the observer's effect. This is the strange phenomenon where just the act of observing a particle changes its behavior. Imagine a photon traveling as a wave, but the moment you try to measure it, it collapses into a particle. This is not something that happens in our macroscopic world, but in the quantum realm, it's just another day at the office. These phenomena, as puzzling as they may be, lead us to a concept that seems like it's straight out of a science fiction novel, the quantum eraser. But before you start imagining a cosmic pencil eraser, let me assure you, it's even more fascinating than that. But to truly understand it, we must first delve deeper into the quantum world. So, are you ready to take the leap? Stay tuned as we unravel the mysteries of the quantum eraser in our next segment. Until then, keep questioning, keep wondering. These phenomena lead us to a concept that seems like it's straight out of a science fiction novel. The quantum eraser. Imagine you could erase information from the universe and change the past. Sounds impossible, right? But in quantum physics, it's not. So let's dive into the fascinating world of quantum erasers. To understand this, we'll first need to grasp two fundamental principles of quantum physics: wave-particle duality and the observer's effect. If we look at light, for instance, it can behave both as a particle and as a wave. This is what we call wave-particle duality. A particle of light, called a photon, can pass through two slits at the same time, creating an interference pattern just like waves do. But once we measure or observe which slit the photon goes through, it behaves like a particle and the interference pattern disappears. This is known as the observer's effect. Now let's bring in the quantum eraser. The quantum eraser experiment is a more sophisticated version of the double-slit experiment. In this experiment, we add devices that can erase the information about which path the photon took. Here's where things get really strange. When we erase the information about which path the photon took, the interference pattern reappears. The photon seems to know whether the information will be available in the future and adjusts its behavior accordingly, even though this decision is made after the photon has already passed through the slits. This intriguing phenomenon is known as retrocausality. In essence, the quantum eraser experiment tells us something truly mind-boggling about the nature of reality. It suggests that the behavior of particles is not just influenced by their present state, but also by future events. The quantum eraser shows us that particles can act like waves or particles depending on whether the information about their path is available. The quantum world is indeed a realm of mystery and wonder, where the traditional rules of time and space that we're accustomed to simply don't apply. Now that we have a basic understanding, let's delve deeper into the intricacies of the quantum eraser experiment. One of the most fascinating aspects of the quantum eraser experiment is the concept of delayed choice. Imagine you're conducting the experiment, and after the photons have either interfered or not, you make the decision to observe which path they took. The strange part, This seems to retroactively determine whether the photons showed wave-like interference or particle-like behavior. But here's the kicker. While it appears as if we're changing the past, we're not actually breaking any laws of physics. The information about the path choice isn't available until both the interference pattern and the path information are compared, which can only happen after both sets of information have been recorded. So, rest assured, we are not sending information back in time or achieving faster than light communication. This delayed choice quantum eraser experiment showcases a peculiar aspect of quantum mechanics known as entanglement, where particles become linked and the state of one can instantaneously affect the state of the other, regardless of the distance between them. It's as if these entangled particles somehow know what measurement has been made on the other, even across vast distances. However, this doesn't mean that we can use this phenomenon to send information instantly across space. The reason, the outcome of the measurements is random. You can't control whether you'll get a particle or a wave result, so there's no way to encode information. And here's another twist in the tale. All this talk of particles knowing or deciding is just a metaphor. Quantum particles aren't conscious. They don't have minds or intentions. We use these terms to help us visualize what's happening, but remember, the reality of quantum mechanics is much stranger than any metaphor can capture. Even though it can be confusing, remember that in the quantum world, our everyday intuitions don't always apply. So, let's keep exploring, and maybe one day we'll get a little closer to understanding the enigma that is quantum mechanics. So, what does the quantum eraser mean for us and our understanding of the universe? This question takes us into some deep philosophical waters. The quantum eraser experiment is more than just a peculiar physical phenomenon. It opens up a whole new perspective on the nature of reality itself. It's like peeking behind the curtain of the universe and finding out that the stagehands are made of quantum foam and entangled particles. In our everyday lives, we're used to the idea that effects follow causes. You drop a glass, it falls and breaks. Simple, right? But the quantum eraser muddies these waters. It suggests that at the quantum level, cause and effect can become entangled, intertwined in ways that defy our classical understanding. The effect can, in a sense, reach back in time and change the cause. This is mind-boggling, and it challenges our very notion of time and causality. But remember, this doesn't mean that we can start predicting lottery numbers or changing our past mistakes. This is happening on a quantum scale, far removed from our macroscopic world. The quantum eraser also raises interesting questions about the role of the observer in quantum mechanics. In the experiment, the choice to observe or not observe the which path information determines the outcome. This suggests an active role for the observer, a concept that has fueled much debate among physicists and philosophers alike. Does this mean that consciousness plays a part in shaping reality? Some interpret it this way, though this is a controversial view. Others argue that it's not consciousness per se, but rather the act of measurement that causes the wave function to collapse. These implications of the quantum eraser are still hotly debated, and there's much we don't understand. But one thing is clear. The quantum world doesn't play by the rules we're used to. It's a realm of probabilities, superpositions, and entanglement, where particles can be in two places at once and effects can precede their causes. The quantum eraser truly shows us that the quantum world is far stranger than we could ever imagine. We've traversed through the quantum realm, and we've seen some truly mind-bending phenomena. Let's take a moment to retrace our steps and ponder over what we've learned. We began our journey by entering the quantum realm, a world that defies our everyday logic. Here, particles can be in two places at once, and they can even change their state instantly, no matter the distance. We then moved on to understand the quantum eraser, a paradox that pushes the boundaries of our understanding. In the quantum eraser experiment, we saw how particles behave like waves, creating an interference pattern until we decide to measure which path they took. The moment we make the decision to observe, the particles seem to know, and they start behaving like individual particles again. This phenomenon, where measurement determines the state of a quantum system, is called wave-particle duality. We delved deeper into the intricacies of the quantum eraser, exploring how it challenges our perception of time and causality. In the delayed choice version of the experiment, the decision to measure or not measure seems to affect the past behavior of the particles. This backward-in-time effect, where future actions appear to change past events, is known as retrocausality. We then discussed the implications of the quantum eraser from the philosophical to the practical. It reminds us that our universe is not as deterministic as we might think. It also holds potential for advancing technologies like quantum computing and quantum cryptography. As we wrap up our journey, I encourage you to continue exploring the quantum realm. Keep delving into its mysteries. Keep challenging your understanding of the universe. There is so much more to learn, and every piece of knowledge brings us closer to the ultimate truth. Remember, in the quantum world, nothing is as it seems. Until our next quantum journey, keep exploring, keep learning, and keep questioning.